Welcome to Optical Fiber Communication Laboratory Manual Practical 10. Request to like, subscribe, press bell icon, share and comment. This is a sample of certificate. Index. In earlier video, we have discussed example related to optical fiber waveguide, transmission characteristic of optical fibers and cables, optical fiber connection, joints, couplers and isolator, optical source, the laser, optical source LED, optical detector, digital transmission system and optical amplifier. In today's session, we will discuss Scilab code for a given example of optical fiber measurement. Practical 10. Optical fiber measurement. Aim: to write a Scilab code for a given example of optical fiber measurement. Software Scilab 6.1.0. Theory: test parameter. Optical test equipment or optical measuring instrument are used to measure and characterize the physical property of the light. The insatiable demand for a high capacity and communication network has fueled the need for highly precise optical test solution. Figure 10.1 important test parameter in WDM link is indicated. In power, optical source, multiplexer, power in, output, spectrum, peak, wavelength, pulse width, extinction ratio is there with insertion loss and channel width, optical amplifier with a gain versus wavelength, AAC noise, pump status, fiber with attenuation, mode field diameter, chromatic dispersion, PMD and fault location, OADM with insertion loss and channel width, DMUX, then insertion loss and spectral response at optical fiber filters, then optical receiver with eye diagram, BER, jitter, response time and responsivity. Some widely used optical system test instrument and their function listed in table 8.1. Test instrument: test support laser, multiple wavelength or broadband. Function is assist in the test that measures the wavelength dependent response of an optical component or link. Optical spectrum analyzer: measure optical power as a function of wavelength. Multifunction optical test system: factory or field instrument with exchangeable module for performing a variety of measurements. Optical power attenuator: reduce power level to prevent instrument damage or to avoid overload distortion in the measurement. Conformance analyzer: measure optical receiver performance in accordance with standard based specification. Visual field indicator: use visible light to give a quick indication of a break in an optical fiber. Optical power meter: measure optical power over a selected wavelength band. BER test equipment: use a standard eye pattern mask to evaluate the data handling ability of an optical link. OTDR field instrument: measure attenuation, length, connector, splice loss and reflectance levels. Helps locate fiber break. Optical return loss tester: measure total reverse power in relation to total forward power at a particular point. Measurement standard: primary standard. Primary standards are used to measure the basic physical parameters such as attenuation, mode field diameter for a single mode fiber, bandwidth and optical power. Second, component testing standard. Component testing standard define important tests to gauge the performance of fiber optic component and play established procedure for equipment calibration. Third, system standard. System standard refer to measure method for link and net. Optical time domain reflectometer (OTDR). Fiber optic OTDR is an optoelectric OTDR test equipment used to qualify an optical fiber. It injects a series of optical pulses into the fiber under test and extract from the same end of the fiber light that is reflected back from point along the fiber. Figure 10.2 indicate block diagram for an OTDR with pulse generator, laser diodes, coupler, amplifier, sampling A to D conversion, averaging processing, then time-based control unit, photo detector and laser display unit. OTDR working principle. An OTDR injects a series of optical pulses into the fiber under test and extract the scattered or reflected light from the same end in the fiber. The scattered or reflected light that is gathered back is used to measure various characteristics of the optical fiber. The OTDR measures strength of the return pulse, integrated it as a function of time and plotted as a function of fiber length. First, attenuation measurement. Three basic methods are available for detecting attenuation fiber. The earliest device and most common approach involves measuring the optical power at transmission through a long and a short length of the same fiber using identical input coupling. This method is known as the cutback technique. Figure 10.3 indicate cutback technique with optical source, mode stripper, near and far end with fiber test 10 photodetector. The average loss alpha in decibel per kilometer is given by alpha suffix dB is equal to 10 divided by L1 minus L2, 10 log 10 PO2 by PO1 is equal to 10 L1 minus N2 into log 10 V2 by V1. Equation 10.1. Uncertainty equal to plus or minus 0.2 divided by L1 minus L2. L1 original fiber length, L2 cutback fiber length, P01 and P02 is a corresponding output optical power at a specific wavelength from the original and cutback fiber length. V1 is the output voltage from the original fiber length, V2 is the output voltage from the cutback fiber length. Second, fiber scattering loss measurement. For cable with a connector, one cannot use the cutback method. In this case, one commonly uses an insertion loss technique. This is less accurate than the cutback method but is intended for field measurement to give the total attenuation for cable ascension cable, where alpha suffix SC is equal to 4.343 10 raised to 5 L into semi Vs divided by V optical dB per kilometer, equation 10.3, where Vs and V optical are the voltage reading corresponding to the scattered optical power and the total optical power within the fiber at the cell. 3. Fiber dispersion measurement. The 3 dB pulse broadening may be obtained using equation 10.4. Tau 3 dB is equal to tau 0 square 3 dB minus tau I square 3 dB 1 by 2 divided by L nanosecond per kilometer, where Ti 3 dB and Tau 3 dB are the 3 dB pulse width at the fiber input and output respectively, and tau 3 dB is width of the fiber impulse response, again measured at the half the maximum amplitude. L is the fiber length in kilometer. It must be noted that if a long fiber is cut back to a short length in order to take the input pulse with measurement, then L corresponds to the difference between the two fiber lengths in kilometer. The 3 dB optical bandwidth for the fiber B opt may be calculated using the equation 10.5. It is a B opt into tau 3 dB is equal to 0.44 GHz nanosecond, 0.44 MHz picosecond. Fourth, fiber cutoff wavelength measurement. The number of guided mode mg is calculated using 10.6. mg is equal to pi a divided by lambda whole square n1 square minus n2 square, where mg is equal to number of guided mode, a is the core radius, n1 and n2 the core peak and cladding indices respectively. Fifth, fiber numerical aperture measurement. The numerical aperture is also determined directly by n is equal to sin theta a by 2 divided by a by 2 square plus d square raised to 1 by 2, or equal to 1 a upon a square plus 4d square 1 by 2, equation 10.7, where a is a pattern size on the screen measured using a calibrated vernier caliper, and d is a far field pattern from the fiber is displayed on the screen, which is positioned at non-distance from the fiber output end phase. Optical signal power can be expressed in decibel using equation 10.8. dB is equal to 10 log 10 P out divided by PR, where PO is equal to received optical signal power, PR is a reference power level. For a 1 milliwatt reference power level, dBm equal to 10 log 10 PO is equal to 1 milliwatt, equation 10.9, and for 1 microwatt reference power level, dB micro equal to 10 log 10 PO divided by 1 microwatt, 10.10 equation. Question 1. A 2 km length of multimode fiber is attached to apertures for a spectral loss measurement. The measured output voltage from the photoreceiver using the full 2 km fiber length is 2.1 volt at a wavelength of 0.85 micrometer. When the fiber is then cut back to leave a 2 meter length, the output voltage increases to 10.7 volt. Determine the attenuation per kilometer for the fiber at a wavelength of 0.85 micrometer and estimate the accuracy of the result. So we would use data as per given one and use equation 10.1 and 10.2 to solve this particular example. So clearance CLC for clearing a variable browser and console, then L1 is equal to 2 into 10 raised to 3 meters initial length, L2 is equal to 2 meters final length, V1 is equal to 2.1 volts initial output voltage, V2 is equal to 10.7 volts final output voltage. Use equation 10.1. Alpha dB is equal to 10 divided by L1 minus L2 10 log 10 V2 by V1 attenuation per kilometer. And uncertainty is equal to 0.2 divided by L1 minus L2, uncertainty in measure attenuation. And displaying the result with the help of printf function. So printf attenuation is and printf uncertainty in measure continuation. Let's try to run this code in the side. So the 5 milliwatt of optical power is equivalent to 6.90 dBm, and the 20 microwatt of optical power is equivalent to minus 16.99 dBm. Option B, the 0.03 milliwatt of optical power is equivalent to 4.77 dB micro, and the 800 nanowatt of optical power is equivalent to minus 0.97 dB micro. So that's it. Same result are displayed in this particular document. Conclusion. This experiment about to know what is optical fiber measurement. This experiment is about measurement standard, basic test equipment, and optical power measurement. This experiment also demonstrates mathematical equation with example for optical power measurement with the help of Siler. Note: demonstrated examples are given in Optical Fiber Communication Principle and Practice, John M. Senior, Pearson 3rd edition book, with example number of 40.1, 40.3, 14.4, 14.5 and 14.7. Thank you.